Welcome back, everybody. This is AP Chemistry. This is Unit 9, Section 4. In the last section, we were taking a look at how strong acids and strong bases, when mixed together, are affected in a titration. This unit, as you can see, is about weak acids and strong base titrations. Now, remember what that means, and we've covered this concept multiple times in the last two units, that acetic acid is deemed a weak acid in that it's not giving up all of its hydrogens. In fact, only some of those hydrogens are going to be freed up in solution. It doesn't completely dissociate. Whereas we have our sodium hydroxide, all of those hydroxides are going to be released, and so that's going to be affecting our calculations and the pH of the solution. And so what's going on is we're going to be mixing up these two together, and our major species in all of this is going to end up being our acetic acid, because it doesn't dissociate completely. We will have some of that in there. We will have our sodium ions. Now remember, they don't really do anything. Those column 1 guys, they don't affect anything as a buffer or anything. They're more of a spectator ion, so we can disregard those. The big player in this is going to be the hydroxide and what it does, and then we'll be ending up with the hydroxides. Remember, what they'll be doing is stealing some of those hydrogens and creating water. But once again, water is just kind of an inert thing. It doesn't really play around with anything, and we'll get our acetate that's going to be produced in the process. Okay, so that's what's going on with those particular scenarios. And let's take a look now at what happens when we start our titrations with this. Okay, we're going to be taking a look, first of all, the first scenario is looking at what's happening when we don't add any sodium hydroxide in the first place. In other words, what we're going to be doing is taking our acetate, HC2H3, O2, we're going to be dissociating it in, basically just splitting it up into water, and we're going to be producing hydrogen ions as well as our acetate, C2H3O2. That's with a negative charge, okay? Now, again, we're not adding any hydroxides in here at all, and I want you to be careful because in this problem, we're going to be adding more and more of my sodium hydroxide. That's going to affect my total volume. So let's go ahead and actually just calculate out how many moles of these ions we have. So we started with a 0.1 molar solution. That means I have 0.1 molar solution. That means I have 0.1 moles for every 1 liter of acetic acid, but I don't have 1 liter. I have 0.05 liters. And so I end up with a starting value of 0.005 moles of acetic acid. Okay, what's going to happen is I'm going to be losing a certain amount of the hydrogen ions. We just don't know how much. So that's going to be my X, X, and X here. So that's going to be at equilibrium what I end up with. And so if I'm going to be calculating just my pH with no sodium hydroxide, I have a Ka value of 1.8 times 10 to the negative 5 is going to equal X squared over my 0.005 minus X. Now remember, my Ka is small. I can disregard that X, multiply both sides by 0.005. My X then becomes a 0.0003. pH is the negative log of this, and so my pH ends up being 3.52. Again, I took the negative log of this value, and I got 3.52. That's with no sodium hydroxide being produced at all, okay? So now it's time to start with my titrations. And let's see what happens as I add varying amounts of my sodium hydroxide. Now keep in mind something. As I do this, remember, I'm not going to be having free-floating sodium or hydrogen ions anymore, all right, am I? I'm going to be adding in my hydroxides, and so that's going to end up eating up some of those hydrogens and creating water, okay? So my new equation, if I take a look at this, is going to be the acetic acid and hydroxides are going to be making my water in this case now, and I'm going to be getting some free-floating acetates. Okay, so now we've got everything set and ready to go, but keep in mind, I have 10 milliliters of sodium hydroxide. Well, let's figure out how many moles that is. Okay, so I have 0.10 moles of sodium hydroxide for every 1 liter, but I only have 10 milliliters, which is 0.01 liters. And so I end up with a starting value of hydroxides as 0.001. Okay, remember I had a 0.005 just a moment ago. That's how much I'm going to be starting with every time. Now, when I do this, I have no acetates to begin with, and so I'm going to be eating up some of these hydrogens using my hydroxides. And so my change is going to be using up this, that will subtract off some of my hydrogen ions with this, and that'll add to this side, isn't it? Okay, so 0.001 on this side. Okay, that's my change. And so at the end, at equilibrium, I have, in fact, 0.004, 0, and 0.001 of my product. Remember, this is going to be my base. Okay, this is my acid. Okay, so now I take a look, and I can't just move into finding pH from here, because remember, these are moles of acetate. Now, how do I find the molarity? Well, I've got to take a look at how much I've got for total solution. I had 50 milliliters plus another 10 milliliters. That ends up being 60 milliliters, which is 0.06 liters. Okay, so if I do that, I end up with 0.004 divided by 0.06. That gives me a 0.07 molar solution. I do the same on this side, 0.06, and I end up with a value of 0.017. Now comes Henderson-Hasselbalch. Okay, the Henderson-Hasselbalch is taking a look at the pH equals the pKa plus the log of your base over your acid. Well, my base is here, which is a 0.017. And my acid is over here, which is a 0.07. Now again, remember how we find the pKa. Okay, this is key. There's just little things along the way we've got to keep in mind. To find pKa, that is the negative log of my Ka value. Okay, we're given my Ka value, so if I take the negative log of that, I end up with a pKa of 4.74. Okay, so now I can take 4.74 plus the log of 0.017 over 0.07. And so if I do that, I end up with a pH of 4.13. Okay. Remember, when I had no sodium hydroxide in there, I started out with a pH of 3.52. So notice that it went up a little bit, didn't it? Okay. Adding in that base has made an effect. Okay. Now let's go ahead and we'll increase the amount that I've got. Okay, I'm not going to erase everything every single time because we're just going to be changing a couple of values along the way. Okay, but we're going to start by just kind of going slow and seeing how all this works. Okay, so we are going to be taking a look. I am starting at the same amount of my acetic acid, but this time I'm adding 25 milliliters of sodium hydroxide. Okay, so I had 0.1 molars. That's going to be moles per liter. And we're going to be this time adding 0.025 liters. Okay, so that's going to give me a value of 0.0025. And again, we're starting with 0 acetate. Okay, so now I'm going to be using up my hydroxide, 0.0025. I'm going to take out 0.0025, and I'm going to be ending up with, at equilibrium, I'm going to be ending up with 0.0025. Okay, there's 0 here. I'm going to be adding 0.0025 to this side. Okay, now the difference is I have 50 milliliters plus 25 milliliters. So that's going to be divided by 0.075 on both sides. So what I have in this solution at equilibrium, what I have is a 0.03 molar solution of my acid, and I have a 0.03 molar solution of my base. Okay, remember that my pKa was 4.74, and so if I do this math, I see that I have my pH is going to be my pKa, which we said was 4.74, and that's going to be added to the log of my 0.03 over 0.03. Okay, if I do that, the log of 1 is 0, and so my pH ends up being 4.74. Okay, so it's adding just a little bit in there. Okay, now all I need to do is change a couple of these values. Okay, and that also changes the solution total right here. This is going to be affected. And so these are the components that we're just going to be playing around with as we add more and more in. Okay, so I had 40 milliliters total, and so 0.10 times 0.04, that will give me a value of 0.04. Okay, no, 0.004. Okay, so 0.004 is my starting value. I'm going to be eating up And so that's 0.004 here. And so that will change that value along the way. Okay, so I'm going to be ending up with 0.001. Not very much of my acetate is left over. Then that adds to my 0.004 on this side, and so I have 0.004. Now remember, this step is the vital step. I have 50 plus 40 milliliters. That's a zero point 0.9 liter. Okay, 0.9 liter here. So 0.001 times the 0.09 liters. Sorry about that. So that's 90 milliliters, which is 0.09. That ends up with a 0.01 molar solution. And this ends up being, let's see, roughly a 0.04. Okay, I'm just rounding that one up a little bit for the sake of ease. And so what happens with this is that changes these values, and that ends up being 0.01 divided by roughly 0.04. I know it's not exactly with that, but it's close enough because of the rounding. And so what ends up happening is my pH is this plus the log of this. Now my pH ends up being 5.34. Okay, now remember, we're really close to that equivalence point because I only had 0.001 moles of my acetate in the solution. Okay, so let's take a look now as we add just a little bit more in there. All right, so that's going to change this part. That's going to change this part. And that changes all of this. All right, so the next step, we're going to be taking a look and adding 50 milliliters of sodium hydroxide. So I had 0.1 molar solution, and that's going to be 0.05 in there. So I have 0.005 molar solution, or moles floating around in there. So that's 0.005 now. And remember, that's equal to this. So I know that we're at my equivalence point, okay? Because my hydroxides equal my acids, I'm equal, and so I'm at my equivalence point. I'm going to be subtracting off. It's going to take away just as much of the hydrogens as the hydroxides are in there. That adds to the 0.005 here. Notice that because it's a weak acid, if I use my Henderson-Hasselbalch, because this is 0 and this is 0, that doesn't automatically make a pH of 7. Because I do have 0.005 at equilibrium, I have 0.005 acetates. Now be careful, that's moles, that's not total molarity, because I have 0.1 liter of solution in here. So I have at equilibrium 0.05 molar solution. Okay, so using the Henderson-Hasselbalch, I could take a look at that way, which is kind of weird because I don't really see any value in that because it's 4.74 plus the log of 0.05 over 0. I can't do that, can I? I can't use the Henderson-Hasselbalch in this case. However, I can, if I know my Ka is 1.8 times 10 to the negative 5, I can take a look at this, and if I take 1 times 10 to the negative 14, and I divide it by the 1.8 times 10 to the negative 5, then I see that my Kb value ends up being 5.6 times 10 to the negative 10. Okay, I do know that if I'm at my equivalence point, that my 5.6 times 10 to the negative 10, that is going to equal x squared, because it's going to be changing, a certain amount in there. It's going to be that 0.005, but it's going to be over 0.05 minus x. Okay, again, this is a small value. Multiply both sides by 0.05. I end up with a value of x equaling 5.3 times 10 to the negative 6th. If I plug that value in, I will be finding a pOH, won't I? A negative log of this number will give me a pOH. That'll give me an answer of 5.28. Well, if I subtract that from 14, I end up with a pH being 8.72. See, Henderson-Hasselbalch will actually fall apart because I don't have any values to work with this. So I do have to go back to the more traditional way of doing this. Okay, so that's how we solve with that one. And we're going to be using that technique from here on out, taking a look at how do we, because I'm past my tipping point, I'm going to be adding more hydroxides than I have with acids. And so really, I'm going to be working with my Kb value along the way. Okay, and so let's take a look at how this might work as we're working through this process. Okay, so I'm now going back to my chart. I now have more hydroxides than I need. Okay, I'm past that point in there. And so let's take a look at what we can be doing with this. All right, so I have zero point 0.06. I have, sorry, zero point 0.1 molar solution. So zero point 0.1 times my zero point 0.06, that will give me a value of 0.006 moles of hydroxide. Okay, so I'm starting with 0.006. Now this time I'm going to be using up all of my acids, and I'm going to be having some hydroxides left over. And so I'm going to be subtracting off 0.005, and I'm going to be adding 0.005 on this side. Okay, once again, I'm using up all my acid to try to neutralize the excess hydroxide. Okay, so if I do that, I end up with 0, a 0.001, and this ends up being a 0.005. Now remember, I don't have, that's not molarity, that's moles in there. And so I started with 50 mils, and now I have 60 mils here, and so that gives me 0.110 liters, 0.110 liters here. Okay, so this will give me a value of 0.009, and this will give me a value of 0.045. Okay, so if I take a look at this way and I see that I've got my hydroxides, I see that I have a pOH is going to be the negative log of this, of the 0.009. I don't really worry about this because it's really the hydroxides that are going to be doing that. My acetate is not going to be stealing any of those away. So I can just run it this way, and I see that my pOH then ends up being 2.05. Okay. Again, this isn't going to be affecting. There's nothing to affect my my pH at this point. So I can just run straight pOH from this, and so I subtract that from 14. My pH ends up being 11.95 then. Okay, pretty cool part because I just found my hydroxides. I didn't even care about the acetates anymore because that's a non-issue for affecting, because my acetate is a conjugate base, and so we're just looking at the potential to pull that back. Okay, so we have one more scenario that we're going to be running off of this on my last titration. Okay, and that's going to be when I add 75 mils. I know I'm over the top, and so I'm going to be adding in a 0.1 times the 0.075. That gives me a value of, let's see here, that gives me a value of 0.0075. Okay, so 0.0075 goes here. And I'm going to use all my acid up to get that 0.0075, and I'm going to add in 0.0075 on this side. And so now I end up with, oops, I'm sorry, this subtract off the 0.005 and 0.005 on this side. Okay, so now I end up with a 0.0025 left over. Okay. 0.0025, there we go, and 0.005 on this side. Okay, now the last thing I have to account for, how much is going to be in solution. That's a 0.125 liters total, 0.125 liters total. That gives me a value of 0.04 molarity, and this gives me a value of 0.02 molarity. Okay, pOH is the negative log of 0.02. The pOH is going to be a 1.7, which means that my pH, if I just subtract the 1.7 from 14, the pH is going to be a 12.3. And there we have all of our titrations of a weak acid and a strong base. All right, you guys should have enough to be going on, and we're going to be doing some labs with this one.